Hi there, welcome to Math 7. This is Unit 2, Lesson 11, Interpreting Graphs of Proportional Relationships. Let's read the stories from the graphs of proportional relationships. So here we go. We're going to have some graphs here that demonstrate a proportional relationship, and we're going to have to talk about what's going on there. Okay, so it says, first of all, invent a situation that could be represented by this graph. We don't know what it is. We can just make it up. We have a point here. We have a point here at 16, 12. Okay, and this could really be anything. This could be Tom's walk, how far Tom is walking. And we know that after 16 minutes, Tom has walked 12, I don't know, 12, maybe more like Tom's drive. Let's do Tom's drive. Let's say he walked 12 miles. That's pretty fast. He is an Olympic athlete. So we can call this Tom's drive. And this over here could be our miles. Okay, so after 16 minutes, Tom has gone on a drive 12 miles. Okay, so it could be anything. So Tom's drive, and we could say that Tom drives 12 miles after 16 minutes. Okay, you can make up anything. But you label your axes, minutes and miles, for how that's going to work there. You give it a title, Tom's drive, and there's a point in the graph. What are the coordinates? We did that already, 16, 12, and it represents how far he had gone after 16 minutes. So a graph allows us to talk about events that are happening. And if we have a constant line here, or that constant proportionality, and there's a proportional relationship, it means that whatever Tom is doing, in this case here, or anyone you have in your story, it's doing it at a consistent rate, a consistent speed, over a consistent point of period of time, and there's no variance there. Okay? So that's what we're looking at today in today's lesson. In part 2, you talked about Tyler's walk. Okay? And like we did before, Tyler was at the amusement park, and he walked at a steady pace from the ticket booth to the bumper cars. The point of the graph shows his arrival to the bumper cars. In 40 seconds, it took him to get there 50 meters. So 50 meters, he got there in 40 seconds. So what's it tell us? It tells us how far he went in 40 seconds. In our case here, that's going to be 50 meters. That's how far he went. Okay? And so you could use that information to get you other times too. We could say if that was at a constant rate, a steady pace, we could actually take our our ruler, and we could line this up like so, and we could find out, okay, are there other points at which we can see where he was at? So for example, at about 15 minutes, well, 25 minutes, we're at, should be at, no, sorry. At 20 minutes, we should be at 25, which is right about there. Okay, so that's about halfway. So 20 minutes, he's gone 25 meters. And so you could find some points along that line as well if you were to graph that out. Okay, let's take a look down here, because now, oh, look, there's more. The table representing Tyler's walk shows other values of time and distance. Complete the table. Next, plot the pairs of values on the grid. So here's 20 and 25, we just did that one. 30 and 37.5 is going to be about here. So that's that one there. 30, 37.5. And it's okay to have decimals, that's fine. And there's 45. 1, I'm not sure what 1 is going to be quite yet, but we'll get there in a second. What does 0.00 mean in this situation? That really is going to be our starting point, right? And that means that before he began walking, he hadn't gone anywhere. And time hadn't started yet. So he starts here where time hasn't begun, and he's still standing next to the ticket booth. He hasn't gone anywhere. This is ticket booth, this is bumper cars. Bumper cars. So that's how far he's gone. Bumper cars are going to be 50 away, so that's where he wants to get to. So that represents his starting point before he had any time had passed and he hadn't gone anywhere. How far away from the ticket booth was Tyler after 1 second? That 1 second is going to become our rate, okay? Or yeah, our rate for how fast he's going. To do that, what we want to do is we take a look at finding our constant proportionality. Let's take our 50 over 40, and we'll do it 50 over 40, which becomes 5/4. That is our constant proportionality. So our rate here would be 5 over 4. Now I'm not sure what 5 over 4 looks like exactly, but if I write that as a decimal, I end up with 1.25. Okay? So in terms of where that would be, this is 5, here's 1, and 1.25 is somewhere, down here. Pretty low. On that line, but way down there. So it's going to be at 1.25 meters. That's how far he walks in 1 second. Okay? So what is the constant proportionality for the relationship between the time and distance? Our k value is 1.25. And what's it tell you about his walk? It says that he walks 1.25 meters per second. Okay? That's the rate at which he is walking on this little journey of his to get from the ticket booth to the bumper cars. You must like them. Alright, next, we gotta look here. If Tyler wanted to get the bumper cars in half the time, how would the graph representing his walk change? So he's gonna be going faster, right? If he's gonna be walking faster, then our graph is gonna go steeper because he's gonna ride at 50 faster. Okay, so we'd have a steeper line there. Okay, what would how would the table change? It would look a little different as well. The numbers would go higher. Our y values would increase at a faster rate, and our constant proportionality would also be larger, maybe greater because it's growing faster. So instead of 1.25 meters per second, maybe he's going faster. It's going to be double that, so he's going to go 2.50 meters per second. If he's going to cut that time in half, he has to walk twice as fast. So it would increase and double that up there. All right, 11.3. Seagulls eat what? 4 seagulls ate 10 pounds of garbage. Assume this information describes a proportional relationship. So 4 seagulls eat 10 pounds of garbage. Plot a point that shows the number of seagulls and the amount of garbage they ate. Okay, so here's 4 seagulls, and we know that the 4 seagulls ate 10 pounds of garbage. Awesome, there it is. There's our 4, 10. Check. Use a straight edge to draw a line through this point and the origin. So we're going to start there, and we're going to come down here to our origin and connect our dots there. Alright, and we have something that looks like that. Okay, plot point 1, k on the line. Well, 1, k is somewhere right about here. Okay, that's our 1, k value right there. What does the value of k tell you about this context? Well, the k is going to be our constant proportionality. What that tells us is, in this case here, if I did 10 over 4, y over x, 10 over 4 becomes, in this case, 2.5. What that tells me as a k value is that 1 seagull eats 2.5 pounds of garbage. And that's what this point tells me. My constant proportionality there tells me that 1 seagull eats 2.5 pounds of garbage. And that's the point of that graph there. So I could use that value to figure out how much any seagull, or number of seagulls will eat. If I knew 4 was 10, then 1 is at 2.5, sorry. I could find out how many 100 are going to eat. I could take 100 and I can multiply it by 2.5 to find out how much garbage 100 seagulls could devour. Lucky seagulls. So our summary for today's lesson, summary here, is that a relationship in the table can be set up with an x and a y, and we can use this to find out that a constant proportionality, that y over x value, is going to be a consistent proportion describing a proportional relationship between two values there. Okay, and so when x is 1, that tells you what the constant proportionality is going to be whenever you get that 1 value. It's the same as setting up like that, and that's just the way it looks in a table. As an equation, what that looks like is it's set up this way: y equals 5/4 x. So that becomes the equation that represents that relationship. Y equals 5/4 x. We can take that relationship and we can graph those things up. We took the same information right here. We can use that table then to create a graph to represent different things. Because it's proportional, we see that again that it's in a line going like that. It's also going to the origin still, and we can find the constant proportionality by looking at that graph. We can look at the value at 1 and find the constant proportionality there. That's our k value. Or I could take a value like this, like we said, and divide y over x, find the quotient of y over y and x, and I can get the constant proportionality there. And I can do that with any point on the line to prove that it is going to be true again and again. All right, so we're going to pause there. You're going to work on your homework and then come back and check to see how you